A visitor from beyond our solar system just spoke. For the very first time in human history, we've received an unambiguous signal from an object originating outside our solar system. This isn't the faint whisper of a distant star, nor the echo of a planet billions of miles away. It is a clear, irrefutable radio transmission originating from a celestial body that has barged into our cosmic neighborhood from the interstellar void. This object is 3 Atlas. It has drifted, in silence, for tens of thousands of years, only to suddenly speak up now. Why choose this exact moment? What secrets lie behind this transmission? Let's be clear, this isn't some cheesy science fiction plot, nor is it wild speculation. The data comes from Earth's most sophisticated radio telescope arrays, verified repeatedly by astronomers who have dedicated their lives to distinguishing cosmic noise from genuine celestial phenomena. The signal is real, and its source has been pinpointed. But this discovery is overturning everything we thought we knew about interstellar visitors. I bet you are thinking exactly what everyone else thought when the news first broke. An alien probe, a technological artifact from an extraterrestrial civilization. This is the first contact humanity has been waiting for ever since we first looked up at the stars. I completely understand the impulse. I thought the same thing initially. But the real story is way more compelling than a simple alien narrative, because the truth behind the signal holds profound mysteries about the universe that we previously knew nothing about. Before the reveal, you need to understand just how revolutionary this discovery is, enough to make scientists rewrite the textbooks. From the moment 3 Atlas entered the solar system, it was an enigma. It's completely different from the planets and asteroids that formed alongside the Sunday 4 billion years ago. It is through and through an alien visitor. Before being gently pulled into our territory by the Sunday's gravity, it likely drifted through the darkness between the stars for millions of years. When astronomers confirmed it as the 3rd verified interstellar visitor in history, the entire scientific community held its breath. After all, the debate sparked by the first interstellar visitor, Oumuamua, still hasn't settled. Some say it was just a peculiar comet, but another group of scientists found that its acceleration and shape simply didn't conform to the laws governing natural celestial bodies. The mystery of Oumuamua already told us, interstellar visitors never play by our solar system's rules. So, when 3 Atlas appeared, astronomers initiated comprehensive monitoring using every tool available, fearing that if it slipped away, we might never get another chance to study it. Multiple telescopes tracked its trajectory, spectrometers analyzed the light reflected from its surface, and observers recorded changes in its brightness as it tumbled. But months passed in total silence, no radio emissions, no anomalous energy signals. Apart from reflecting sunlight, it seemed like just another dirty snowball drifting through the void. The turning point arrived in October of 2025. On the screens of South Africa's MeerKAT precision radio telescope array, something appeared that made astronomers gasp. A radio signal at a specific frequency was emanating from the direction of 3 Atlas. Not random noise, not Earth-based interference, but a clear emission at a wavelength of 18 centimeters. This is the exclusive frequency of the hydroxyl radical, the O molecule formed when water is broken down by intense solar radiation. By now, your imagination must be running wild. An interstellar object sending a signal. Isn't this the beginning of first contact? Don't get too excited just yet. This discovery is far more interesting than the story of an alien probe. This signal tells us that 3 Atlas is alive, not biologically alive, nor technically operational, but dynamically active on a chemical level. This activity is revealing the secrets of its birth in another star system, secrets we previously couldn't even dare to imagine. The hydroxyl signal detected by MeerKAT indicates that 3 Atlas is outgassing. The water, ice-locked inside it for millions, perhaps billions of years, is now sublimating directly from solid to gas. As it approached the Sunday, reaching its perihelion, closest point to the Sunday, the solar radiation became intense enough to break down the water. The resulting hydroxyl radicals then broadcast signals at a specific radio frequency, detectable by telescopes even millions of miles away. This is the voice of 3 Atlas, not an alien code, not a navigation beacon, but an ancient comet from an unfamiliar star system, revealing its chemical secrets for the first time using natural radio signals. But why now? Why remain silent for so long? Only to speak at this precise moment, the answer lies in the love-hate relationship between the comet and the Sunday. While 3 Atlas drifted in the extreme cold of the outer solar system, it was dormant, Solar radiation was too weak to melt the ice in its nucleus. But once it approached the Sunday, crossing a certain heating threshold, this interstellar visitor awakened. The ice sublimated directly into gas. It doesn't melt in the vacuum of space. Water was broken down into hydroxyl radicals, and it began to broadcast its presence to the entire universe. You have to truly grasp how incredible this moment is. We are observing the chemical transformation of matter from another solar system in real time. The water molecules generating this signal were not formed around our Sunday. They condensed in the protoplanetary disk of another star. That star system might be hundreds of light years away from Earth, having birth planets and comets we will never see. And now the water from there is greeting us using the universal language of physics and chemistry. This discovery confirms what astronomers have suspected for years. 3 Atlas is almost certainly an interstellar comet, not an asteroid. Not a planetary fragment, but a primordial mixture of ice and rock. Its frozen core holds the chemical fingerprint of the star system where it was born, and this fingerprint is being transmitted to Earth in the form of hydroxyl signals, telling us a crucial piece of information. It contains a significant amount of water, one of the most fundamental molecules in the universe and the key to the existence of life. Think about how low the probability is in human history. Only 3 interstellar objects have been confirmed entering the solar system, 3 visitors from the vast cosmic ocean, and 3 Atlas allows us to do more than just observe from afar. We are listening to its chemical voice, unlocking its secrets in an unprecedented way. This is the first time humanity has detected a radio signal from an interstellar comet, and this first time is happening now, in your lifetime. In this brief window, 3 Atlas is close enough to the Sunday to be activated, and close enough to Earth for our telescopes to capture the signal. The scientific community is buzzing. Research papers are being rushed out, and data from multiple observation platforms is piling up, because this signal is not just a discovery. It has unlocked the future of interstellar visitor research. It proves that radio astronomy can penetrate the chemical composition of extrasolar objects, something optical observation simply cannot do. Our ability to study the universe has just turned a new page. But I can see the doubt in your eyes. How can we be sure it is just a natural comet? Could there be a more complex inside story? Good question. That is the attitude of rational exploration. Next, I will take you through the truth of the data, tell you what science actually says, and why the natural origin story is far more shocking than the artificial creation story. Because to understand this signal, we must first understand the scientific principles of hydroxyl emission, the nature of comet outgassing, and the coincidental conditions that allowed all this to be detected. And this journey of revelation must begin with the laws of physics and chemistry that support this signal. To understand what 3 Atlas is saying, you first have to understand its language. This language is written in the physical laws of molecular bonds, hidden in the interaction between ice and radiation, and manifested in the exclusive frequency of hydroxyl radicals in the space environment. This is not abstract theory. We have verified these measurable, predictable scientific laws thousands of times on comets within our own solar system. The only difference is, this time, we are applying this knowledge to an alien visitor. Let's first look at a comet's transformation as it approaches the Sunday. Deep within the nucleus, water molecules, too, are locked in a frozen matrix of rock and ice. In the extreme cold of the outer solar system, these molecules exist as solid crystals, unchanged for billions of years. The comet is like a flying iceberg, preserving the chemical environment of its birth intact. But once the comet's orbit brings it closer to the Sunday, everything changes. Solar radiation, especially ultraviolet light, begins to heat the surface of the nucleus. When a certain threshold is reached roughly around Jupiter's orbit, depending on the comet's composition, the ice begins to sublimate. Note, sublimate, not melt. In the vacuum of space, solid ice turns directly into gas, skipping the liquid phase. Water molecules escape from the solid, forming what we see as the comet's coma, a fuzzy layer of gas and dust surrounding the solid nucleus. And the magic of chemistry begins here. After escaping into space, the water molecules are directly exposed to intense solar radiation that couldn't penetrate when they were hidden inside the nucleus. The Sunday's ultraviolet photons strike the water molecules, breaking them apart in a process called photodissociation. The chemical bonds between hydrogen and oxygen break, producing hydroxyl radicals, O molecules. This molecule is extremely reactive and has a special property. It can be detected from vast distances. Hydroxyl radicals emit radio waves at a precise frequency, 1665.402 MHz MHz, corresponding to a wavelength of approximately 18 centimeters. This emission originates from quantum mechanical principles. Molecules exist in different energy states, and when they jump from a high-energy state to a low-energy state, the excess energy is released in the form of a photon at this specific frequency. This is not a random phenomenon, it is as constant as the law of gravity, whether it is a hydroxyl radical formed near Earth or produced in a comet from another star system. The emission frequency is exactly the same. This is a universal cosmic signal that radio astronomers can capture with extremely high precision, and what the MeerKAT telescope captured from 3 Atlas is precisely this signal. The 18-centimeter radio wave is not mysterious, nor is it inexplicable. It is the direct result of the nucleus ice sublimating, being broken down into hydroxyl radicals by solar radiation, and then emitting at its characteristic frequency. We have seen this signal in hundreds of comets within our solar system. The uniqueness of 3 Atlas is not the signal itself, but its origin. This is the first time we have detected this signal from water molecules born outside the Sunday sphere of influence. You must be asking, 3 Atlas has been drifting in the solar system for several months. Why wasn't it detected earlier? The answer lies in the relationship between solar distance and outgassing intensity. Comet outgassing is not uniform. The farther from the Sunday, the weaker the outgassing. As 3 Atlas reached its perihelion in late October 2025, the solar heating intensified dramatically. The sublimation rate soared, more water molecules escaped, more hydroxyl radicals were produced, and the radio signal became strong enough to overcome the background noise of space and be captured by telescopes like MeerKAT. The timing of the detection also reveals secrets about the composition of 3 Atlas. Not all comets can produce such a strong hydroxyl signal. The signal strength depends on the water-ice content of the nucleus, the structure of the ice matrix, and the efficiency of gas release when heated. The fact that MeerKAT could capture a clear signal indicates that 3 Atlas contains a large amount of water ice, comparable to the water ice content of comets in our solar system's Oort cloud. This similarity itself is shocking. It means that the conditions for forming comets in our solar system, the temperatures and chemical processes that lock water into ice cores, also existed in the distant star system where 3 Atlas was born, but the value of this detection goes far beyond confirming the presence of water. The hydroxyl emission data allows astronomers to calculate the outgassing rate, that is, the amount of water the comet loses per second when heated. Preliminary estimates from the MeerKAT data indicate that the outgassing rate of 3 Atlas is consistent with a nucleus several kilometers in diameter, which is typical of long-period comets. This data helps us determine its size and mass details that optical observations alone cannot clarify, because the brightness of the coma completely obscures the faint reflection of the solid nucleus. Radio detection also exposes the distribution of ice within the nucleus. If 3 Atlas were just a solid ball of ice, the outgassing pattern would be completely different from what we observed. The data shows that its structure is more inhomogeneous, ice and rock mixed together, forming a porous matrix through which gas can escape via cracks and channels. This structure perfectly matches the theory of comet formation in protoplanetary disks, ice particles and rock dust, continuously colliding and accumulating over millions of years, forming a layered structure that preserves the chemical diversity of the protoplanetary disk. Even more interesting is the comparison of the hydroxyl signal of 3 Atlas with those of solar system comets. Radio astronomers can capture subtle differences in the emission spectrum, which hide the physical conditions of the coma, such as temperature, density, and gas expansion velocity. Early analysis shows that the hydroxyl signal of 3 Atlas is highly similar to the signals of our solar system comets. The gas expansion velocity is comparable, and the emission profile perfectly matches the expected profile of a comet at this solar distance. Every detail of this signal confirms standard comet physics, except that this set of physical laws is being applied to an alien visitor of extraordinary origin. This is the beauty of science. We spent decades studying solar system comets, establishing a theoretical framework that can accurately predict what kind of radio signal a comet of a certain size will emit at a certain distance from the Sunday. When we pointed the radio telescopes at 3 Atlas, the observational data perfectly matched this framework. There are no anomalies in the emission spectrum, no strange frequencies, no modulation or patterns that could suggest a non-natural origin. The signal is exactly what physics and chemistry predicted, down to the last detail. Besides the signal, 3 Atlas also presented an unforgettable visual spectacle. The anti-tail, a tail that should point away from the Sunday, surprisingly seemed to be pointing towards the Sunday. This sounds like a violation of physical laws after all. The comet tail is clearly pushed out by solar radiation and solar wind, but don't worry, this is actually an easily explainable optical illusion. When Earth is exactly in the comet's orbital plane, we can see the flat dust trail left along its orbit. From our perspective, this trail appears to extend in front of and behind the nucleus, looking like 2 tails, one normally pointing away from the Sunday and the other reversely pointing towards the Sunday. In October 2025, when 3 Atlas passed perihelion, it perfectly staged this scene. Photos from both amateur astronomers and professional observatories clearly captured the double tail spectacle, a normal gas and dust tail pointing away from the Sunday, and another anti-tail pointing straight ahead in the orbit. Some took the opportunity to claim this is evidence of active propulsion, like a rocket firing in both directions, but the truth is purely a matter of geometric perspective, having nothing to do with anomalous activity. Dozens of comets in the solar system have exhibited this phenomenon. As long as the viewing angle is right, this counterintuitive sight can be seen. The size of 3 Atlas has also been a hot topic, though there is still no precise figure. Estimating the size of the nucleus is inherently difficult. What we see as the comet is actually the coma, the cloud of gas and dust surrounding the solid nucleus, which can be thousands of times larger than the nucleus itself. Astronomers estimate its nucleus diameter to be about 1 to 3 kilometers, based on brightness and surface reflectivity. This size is similar to our Oort cloud long-period comets. Not gigantic, but not small either. Of course, this estimate has a large margin of error. If the surface is super dark and has low reflectivity, the nucleus might be larger. If the reflectivity is high, it might be smaller. But this fuzzy size hides crucial information. It relates to its mass and lifespan. A nucleus several kilometers in diameter has enough reserves of ice and rock to survive several perihelion passages in the solar system, retaining a large amount of volatile material, even after drifting in interstellar space for millions of years. This indicates that we are not seeing a small fragment, but a complete giant comet carrying a large material sample from its parent star system. Whatever chemical codes it hides, there is enough quantity, making it a hot commodity in the eyes of astronomers. More complicated is its rotation state. The pattern of changes in the comet's brightness indicates that it is not rotating smoothly around a fixed axis, but rather tumbling. This chaotic rotation is common in comets and asteroids, usually caused by collisions or gravitational interactions. The angular momentum is disturbed. For 3 Atlas, the tumbling might be an after effect of being kicked out of its parent system, for example, a close encounter with a planet or another comet, where gravity not only flung it into interstellar space, but also sent it tumbling adrift. Or it could be the result of outgassing torques over millions of years. Gas erupting from the surface acts like small rockets, slowly changing its rotation state. Putting these characteristics together, high speed, unusual composition, fluctuating brightness, anti-tail, uncertain size, tumbling rotation. Individually, each seems bizarre, but together, they perfectly outline a comet that has experienced a legendary journey. None of these features require a supernatural explanation. They all fit the logic of a natural comet formed in another star system, ejected by gravity, drifted in interstellar darkness for eons, and now coincidentally entered the solar system, luckily observed by us. These anomalies are not evidence of artificial creation, but the marks of alien origin, where alien literally means from elsewhere, carrying secrets from corners of the galaxy we can never directly visit. Once you understand this, you will see 3 Atlas in a new light. It is not just a comet, but a sample return mission delivered to our doorstep. We didn't need to launch a probe. It brought the data from another star system itself, hidden in its composition and behavior. To fully grasp this godsend opportunity, we must first review its discovery journey. See how astronomers turned a faint point of light into the most valuable scientific target. This is not just a story of detecting signals, but a story of human perseverance. A story of global astronomers joining forces to chase the comet. The first appearance of 3 Atlas was several months before the radio signal. At that time, automated survey telescopes scanning the sky for near-Earth threats flagged an object with a bizarre trajectory. It didn't match any known solar system objects, Preliminary calculations showed it was on a hyperbolic trajectory, which immediately raised alarms. A hyperbolic trajectory means it is not bound by the Sunday and likely an interstellar visitor, but early orbit calculations always have errors, and astronomers needed more data to confirm, is it an outsider, or a solar system comet with a very elongated orbit? Follow-up observations quickly ensued. Telescopes around the world pointed at this light spot, continuously measuring its position as it moved against the background of stars. Each measurement made the orbit calculation more precise, and the evidence for an interstellar visitor grew stronger. Weeks later, the conclusion was confirmed. 3 Atlas, the third interstellar object discovered by humanity, and the second interstellar comet after 2, Borisov. This discovery electrified the scientific community because we had more time than we did with Oumuamua. Oumuamua was already on its way out when discovered, while 3 Atlas was still flying towards the inner solar system. This was a golden opportunity to study an alien comet. In the late summer and autumn of 2025, as 3 Atlas flew towards the Sunday, global observatories entered a coordinated monitoring mode. Optical telescopes tracked brightness and analyzed spectra, looking at both the sunlight reflected from the surface and the light emitted by the coma gases. The results detected water vapor, carbon dioxide, carbon monoxide, and various molecules common in comet outgassing, even finding organic compounds in the spectrum, possibly complex carbon-based molecules cooked by radiation in cold space. All clues pointed to a comet, but its interstellar origin made every detail priceless. By mid-October 2025, 3 Atlas was approaching perihelion. Its distance from the Sunday was roughly equivalent to Earth's orbit. This is when the comet is most active, solar heating is strongest, and outgassing is fastest. Astronomers knew this was the last research window. Once it passed perihelion and started its return journey, there would never be such a good opportunity again. Telescopes were booked solid in advance, observation schedules precise to the hour, just to capture everything with different wavelengths and instruments. South Africa's MeerKAT radio telescope also joined the observation. This array of 64 dish antennas is specifically designed to search for hydroxyl signals. Previous interstellar visitors didn't receive this treatment, partly because the telescopes were busy, and partly because those objects were not active enough to emit detectable radio signals. But optical observations of 3 Atlas showed it was outgassing heavily, and astronomers judged if it has water ice, it is highly likely that radio signals can be detected. The moment of successful detection perfectly coincided with perihelion. In late October 2025, MeerKAT captured the 18-centimeter wavelength hydroxyl signal, exactly matching the expected frequency. The signal strength indicated that it was releasing thousands of kilograms of water per second. Solar heat was causing the ice on the entire surface of the nucleus to sublimate. This was a historic breakthrough, humanity's first detection of a radio signal from an interstellar comet, obtaining data that optical observations could never provide. The greatest value of radio detection is the ability to directly calculate the outgassing rate. Optical observations can only see how bright the coma is, but converting brightness to mass loss rate requires assumptions about the ratio of dust to gas, particle size, and other parameters. The hydroxyl signal, however, is a direct measurement. The signal strength is proportional to the number of hydroxyl molecules, and through known photo dissociation laws, the water production rate can be calculated. The MeerKAT data allowed astronomers to finally understand how much flesh 3 Atlas lost during its perihelion passage. Meanwhile, optical telescopes were not idle, taking numerous detailed photos of the coma and tail. The photos showed typical comet structures, the bright central, nuclear region, the nucleus surrounded by dense gas and dust, the coma hundreds of thousands of kilometers wide, and the double tail following the comet, the gas tail ionized by solar radiation, appearing blue under color filters, shaped by the solar wind magnetic field, the dust tail pushed out by radiation pressure from large particles reflecting sunlight in yellowish-white, plus the anti-tail, like a sharp thorn pointing forward, creating a unique spectacle. In early November 2025, 3 Atlas passed perihelion and began moving away from the Sunday. Outgassing gradually weakened, and the hydroxyl signal detected by MeerKAT also weakened, fully consistent with the expectation of decreasing solar heating. The optical brightness was also decreasing, but not a smooth decline. It flared up several times after perihelion, with brightness suddenly soaring and then falling back. This is common in Sunday-baked comets. Thermal stress causes the surface to crack, and the volatile ice hidden inside suddenly erupts. causing the brightness flare-up. Here I must mention the contribution of amateur astronomers. From small telescopes in their backyards to sophisticated private equipment, amateurs worldwide took numerous photos of 3 Atlas, all uploaded to international databases for professional astronomers to use. This distributed observation network achieved almost 24 coverage, perfectly filling the gaps of professional telescopes. After all, any observatory can only observe when the object is above the horizon and the weather is good. It was the collaboration between professionals and amateurs that completely recorded the entire process of the comet passing perihelion. By mid-November 2025, 3 Atlas crossed Earth's orbit, flying towards the outer solar system. The hydroxyl signal was still detectable, but increasingly weaker. The coma was also shrinking, and the detailed observation window was closing. Telescopes began turning to other targets, but would still take a peek occasionally to see if it would behave unexpectedly as it cooled down. Looking back at these few months of chasing the comet, what strikes me most is the efficiency. In such a short time we managed to figure out so much, from the initial discovery of the light spot, to the perihelion passage, and then the return journey. The intensive observation period was only a few months. But in these few months, astronomers collected full-spectrum data from X-rays to radio waves, took thousands of photos, measured chemical composition, tracked structural changes, and achieved the breakthrough of zero in interstellar comet radio detection. This level of global coordinated effort precisely illustrates the high value of its role as an interstellar messenger. Of course, data collection is not completely finished. 3 Atlas is still flying outwards, slowly disappearing from view, but telescopes will watch until the last moment. Every additional measurement adds a bit more knowledge, every additional observation adds a bit more background information. But the most active, most data-productive phase is over. The next step is digestion, extracting every useful piece of information from the massive observations. And the value of this information has long surpassed the scope of studying a single comet. It touches upon the most fundamental questions. How do planetary systems form? How is matter transferred between stars? How do chemical substances evolve in cold space? What secrets of the Milky Way can we learn through wandering objects? This is why 3 Atlas is truly important, and why we must understand its significance. The radio detection of 3 Atlas actually marks the beginning of a new era in astronomy. Interstellar visitors are no longer rare surprises, but regular scientific research subjects. The methods we use to study it, especially hydroxyl signal radio detection, provide an operation manual for future chasing of alien visitors. The significance behind this is far greater than discovering a comet. First, look at the implications for comet formation. 3 Atlas, in its appearance, behavior, and way of signaling, is exactly the same as our Oort cloud comets. This shows that the process of forming comets is universal, at least very similar in different star systems. Theoretically, the physical laws of ice formation and the chemical laws of protoplanetary disks should be the same throughout the universe. But seeing it with your own eyes and theoretical speculation are completely different things. This comet turned theoretical expectations into observational facts. The hydroxyl detection also tells us a crucial piece of information. 3 Atlas has a very high water ice content, which in turn suggests that water may also be common in comets from other star systems. Water is the most basic molecule for life, and the presence of so much water in interstellar comets indicates that the chemical building blocks of life are everywhere in the Milky Way. This doesn't mean life is everywhere in the universe, nor does it mean 3 Atlas brought living things, but it means the chemical diversity of the universe is far beyond imagination, and the raw materials supporting life are not rare at all, not exclusive to Earth or the solar system. Its high carbon dioxide content also hides secrets of its parent system. In our solar system, the ratio of carbon dioxide to water in a comet depends on when and where it formed. Comets formed farther from the Sun, in colder places, have more volatile ice like carbon dioxide. The relatively high carbon dioxide ratio of 3 Atlas may indicate that it formed in the outer regions of its parent system, or that its parent system's protoplanetary disk was colder overall than ours. This kind of cross-star system comparison can only be done by studying alien comets. The impact is not just on the chemical level. Confirming 3 interstellar objects entering the solar system in just a few years directly tells us how high the density of interstellar matter is. With current survey capabilities, several can be discovered each year, considering that only those flying close enough and bright enough can be discovered. The number of interstellar objects near us must be outrageously high. Estimates suggest that at any given time there may be tens of thousands or even millions of interstellar objects in the solar system, but most are too small, too far away, and undetectable by current technology. More crucial evidence comes. Radio astronomy is not just passive watching. By tracking the hydroxyl signal, astronomers can monitor in real time how outgassing evolves as the comet's distance from the Sunday changes. When 3 Atlas passes perihelion and begins to retreat to the cold outer regions of the solar system, outgassing will gradually weaken, and the hydroxyl signal will also weaken, until it crosses the threshold where solar heating is insufficient to sublimate ice. The signal will disappear completely, and the comet will return to dormancy. And now we have observed this predictable pattern. The signal strength changes exactly along the solar distance determination curve without any deviation. This time evolution pattern is the strongest evidence for a natural comet. More convincing than any theory. If it were an artificial transmitter, the characteristics would be completely different. It would not strengthen as it gets closer to the Sunday and weaken as it gets farther away. It would not be exactly at the precise frequency of the hydroxyl transition, nor would it carry the spectral characteristics of gas expansion in a comet coma. The signal matches the comet model too well. To insist on other explanations would mean ignoring the simplest, most data-fitting answer, which is untenable in science. But I understand you still have a shred of reluctance, always wanting some mind-blowing possibility, right? That is perfectly normal. It is this curiosity that drives science forward. But the premise of satisfying curiosity is to look at all the evidence, not just pick the parts you want to believe. So let's face the alien probe hypothesis head on. If 3 Atlas were artificial, what would the data look like? Why does the hydroxyl signal not match an artificial profile at all? After all, to understand what it is, we must first understand what it is not, which requires us to honestly evaluate all alternatives and then choose the conclusion that best fits the evidence. Now, we have to face the elephant in the room, the social media headlines that spread faster than scientific conclusions. As soon as the 3 Atlas signal was revealed, comment sections and conspiracy theory forums exploded. Alien probe, extraterrestrial beacon, we are being watched. You must have scrolled past these headlines, got excited, and wondered if there was any truth in them. Could scientists have missed crucial information, or even deliberately concealed something? Let me tell you clearly, the alien hypothesis not only fails to explain the data, but also completely contradicts the facts we have observed. First, we need to understand what an artificial signal looks like. If 3 Atlas were a probe built by alien intelligence, whether actively operating or dormant, whether intentionally signaling or accidentally leaking radiation, its radio emission characteristics would be vastly different from what we detected. Artificial signals, especially those used for communication or navigation, are mostly narrowband. The energy is concentrated in a very small frequency range, with almost no spread. But the natural signal of the hydroxyl radical has a characteristic spectral profile, where the shape of the spectral line is determined by the physical conditions of the gas cloud, and what the MeerKAT telescope captured is precisely this natural profile. More importantly, an artificial transmitter would have design traces, either stable output or a modulation pattern. Communication signals would have temporal regularities, repeating sequences, or encoded information, manifested as changes in intensity or frequency over time. Navigation beacons might have periodic pulses or frequency sweeps, but the hydroxyl signal of 3 Atlas has none of these. The intensity changes smoothly, only with solar distance, strongest around perihelion, weakening afterwards. There is no modulation, except for the normal fluctuations caused by different faces being illuminated by the Sunday as the comet rotates, and certainly no trace of intentionally encoded information. The frequency itself is also a key clue. If aliens built a transmitter, why would they choose 1660? 5.402 MHz, the exclusive frequency of hydroxyl. This frequency has no special significance for communication, and on Earth, it is even a protected frequency band. Because astronomers rely on it to study the hydroxyl signals of comets and interstellar clouds, transmitters actively avoid it. If designing interstellar communication equipment, they would likely choose a frequency related to fundamental physical constants, such as the 1420 MHz hydrogen line, which is the scientifically recognized universal frequency for interstellar communication. The 18 centimeter hydroxyl frequency is nature's choice, not an engineer's choice. Some also say the timing of the signal is too suspicious. 3 Atlas drifted silently for so long and started signaling as soon as it approached Earth. It must be responding to us. But anyone who understands comet physics knows this claim is baseless. The signal did not appear when it was closed to Earth, but when it was closed to the Sunday. Exactly the time when outgassing theory predicts the hydroxyl signal should be detected. The signal strength is not related to the distance to Earth, but strongly correlated with the distance to the Sunday, and this correlation perfectly matches the mathematical formula of solar heating and sublimation rate, which we have verified countless times with solar system comets. We also need to correct a bias from another star system equals artificial. This is actually a misconception about interstellar space. We always think the space between stars is empty and objects either orbit a star or don't exist. But the truth is, space is full of wandering objects, planets kicked out of their birth systems, comets flung out by gravitational interactions, asteroids ejected during stellar encounters. Simulations show that our Milky Way galaxy alone may have trillions of interstellar objects, more than the number of stars. Occasionally one enters the solar system, which is not a suspicious event at all, but a statistical inevitability. More importantly, we studied 3 Atlas with multiple technologies and instruments. Optical telescopes analyzed surface reflection, finding its rocky, icy composition consistent with solar system comets. Color measurements showed a reddish hue, a typical feature of organic surfaces long exposed to cosmic radiation. The morphology of the coma and tail perfectly matched the laws of natural outgassing, with the trajectories of dust and gas determined entirely by solar radiation pressure and the comet's motion. All data from all instruments point to the same conclusion: a natural comet. I must say fairly, some researchers suggest keeping all possibilities open until there is conclusive evidence, which is correct in principle. Curiosity is the driving force of science, but open-mindedness does not mean all hypotheses are equal. Extraordinary claims require extraordinary evidence. Claiming 3 Atlas is artificial is an extraordinary claim, so you must explain, why does it look like a comet, behave like a comet, and signal like a comet? If you insist it is artificial, you have to add a bunch of extra assumptions, which is the least desirable approach in science. This brings us to Occam's razor: when multiple explanations fit the facts, the one with the fewest assumptions. The simplest is most likely true. The natural comet explanation only requires the physical and chemical laws we have verified for decades, while the alien probe explanation, it requires assuming the existence of an alien civilization, assuming they have mastered interstellar travel technology, assuming they intentionally sent a probe to the solar system, assuming this probe looks exactly like a comet, and assuming its signal perfectly mimics hydroxyl emission. With each additional assumption, the probability drops dramatically. Moreover, the search for extraterrestrial intelligence, SETI itself, is a legitimate scientific field. SETI researchers have spent decades developing technologies to distinguish between artificial signals and natural phenomena. When Oumuamua passed through the solar system, the Breakthrough Listen project specifically monitored it with radio telescopes for a long time, finding no artificial signals. The second interstellar object, too, Borisov, was also monitored in the same way, with the same result. With 3 Atlas, what we found is a clear natural hydroxyl signal, not an artificial transmission. The scientific consensus on 3 Atlas is extremely strong. Researchers from different institutions, using different telescopes and analysis methods, all reach the same conclusion: it is an interstellar comet undergoing normal outgassing as it passes through the inner solar system. This consensus is not intellectual rigidity, but the evidence is overwhelming. In science, evidence-supported consensus is the standard we use to distinguish reliable knowledge from wild guesses. But I think the most interesting point is, the speculation of an alien probe actually devalues the true identity of 3 Atlas. An artificial probe can only tell us a civilization built it, which is certainly shocking, but not very helpful for understanding the universe itself. A natural interstellar comet, on the other hand, it can tell us about the formation laws of other star systems, the chemical commonality of planetary systems throughout the Milky Way, how objects drifting in interstellar space for millions of years evolve. These are the big discoveries that can rewrite our understanding of the universe. The truth about 3 Atlas is, it is a messenger, but it carries not the intentional message of alien engineers, but the chemical code etched into its structure, recording the distant star system where it was born and the environmental conditions during its formation. Speaking of this, new questions arise. If it is just a natural comet, why does it seem so different? Why can it trigger so much speculation? Because although the hydroxyl signal confirms its comet identity, it does have some rare features that are different from the comets we commonly see. These features are not evidence of artificiality, but the marks of its extraordinary journey. After all, it comes from a star system completely different from our own. Understanding these features is the most exciting part of this story. Every comet has its own temperament, but 3 Atlas is considered unconventional even in the comet community. It is precisely these features that fueled speculation, generated headlines, and made some feel things are definitely not that simple. So let's break down these features one by one and see what secrets they reveal about this interstellar visitor. The first thing that caught astronomers' attention was its speed. When first tracked, its speed relative to the Sunday revealed a hyperbolic trajectory, meaning it is not bound by the solar system's gravity, not an elliptical orbit that will return, but a flyby, eventually returning to interstellar space. Even accounting for the acceleration effect of the Sunday's gravity, it still has excess velocity, which is ironclad proof of an alien visitor. It is estimated that its original interstellar speed was about 14 to 17 kilometers per second, fast enough to fly from Earth to the Moon in half an hour. But you must understand, this speed is not evidence of a propulsion system, but evidence of its origin. Objects in interstellar space are not stationary. They orbit the galactic center along with the stars in the Milky Way, with speeds relative to distant galaxies reaching hundreds of kilometers per second. But the relative speeds between stars are usually between 10 and 30 kilometers per second. The speed of 3 Atlas falls exactly within this range, perfectly consistent with the expectation of drifting in interstellar space, accidentally captured by the solar system's gravity. Its trajectory also holds clues. By backtracking its path through space and combining the speed data, astronomers calculated that it roughly came from the direction of the Draco constellation, but that region has no known nearby stars. What does this mean? 3 Atlas may have been drifting in interstellar space for millions of years, long enough that the star system where it was born has long since moved elsewhere due to the Milky Way's rotation. It is an ancient relic from a star system that may have already become unrecognizable. Another feature of interest is its composition, especially the unusually high carbon dioxide content. In the months before perihelion, spectral observations found that it released a large amount of carbon dioxide, indicating that the nucleus contains not only water ice but also a lot of carbon dioxide ice. In solar system comets, carbon dioxide is common, but the content in 3 Atlas seems higher than average. Some say this is evidence of a bizarre origin, but the truth is we have seen too few interstellar comets to know what the normal content of comets from other star systems is. In fact, the high carbon dioxide content tells us a crucial piece of information. Carbon dioxide is more volatile than water, meaning it can sublimate at lower temperatures and farther distances. The fact that 3 Atlas could retain so much carbon dioxide after drifting in interstellar space for millions of years indicates that it remained in an extremely cold environment throughout its journey, preserving these volatile ices. This allows us to see its most pristine composition, much purer than comets that have repeatedly passed through the inner solar system and been baked by the Sunday multiple times. In a sense, 3 Atlas is more authentic than our solar system comets, better reflecting the environment of its birth. Another puzzle is its brightness variation fluctuating unpredictably. A few months before perihelion, it suddenly brightened significantly, becoming exceptionally clear in telescopes, and then dimmed again after a while. Such outbursts are common in comets, usually caused by the nucleus suddenly releasing a large amount of gas and dust, possibly due to surface structure collapse or exposure of fresh ice after the surface layer sublimated. But the timing and intensity of the outbursts of 3 Atlas do not fit the pattern predictable solely by solar distance. This unpredictability has sparked much speculation. Is there special activity inside? Is the nucleus structure different? These speculations might be correct, but they have nothing to do with artificiality. The nucleus is inherently not a uniform sphere, but a mixture of ice, rock, and organic matter formed by collisions over millions of years in the protoplanetary disk. Some places have more ice, some more rock. Some places have highly volatile ice-like carbon monoxide and nitrogen, which will explosively sublimate at specific temperatures. Coupled with the comet's rotation, different faces are illuminated by the Sunday, causing outgassing to fluctuate in strength. reflected on Earth as fluctuating brightness. This understanding reshapes our view of the solar system's boundaries. The traditional picture of the solar system planets orbiting the Sunday, a neat collection bounded beyond Neptune or in the Oort cloud, is incomplete. In reality, our solar system is frequently visited by matter from elsewhere. A continuous stream of interstellar material passes through, occasionally close enough for us to detect. We are not isolated. We are part of a galactic ecosystem, with matter cycling between star systems, carried by the gentle gravitational currents of the Milky Way. The radio detection method, verified by 3 Atlas, opens up new possibilities for detecting and characterizing future interstellar comets. Radio telescopes can observe objects under conditions difficult for optical telescopes, such as during the day or when the object is close to the Sunday. Radio observations also provide data on composition and activity, not easily captured by optical observations. As radio telescope technology continues to improve, with arrays like MeerKAT and the upcoming Square-Kilometre Array, SCARE, coming online with unprecedented sensitivity, we will be able to detect hydroxyl emissions from dimmer, more distant objects, expanding our ability to study interstellar visitors. Another exciting possibility is that 3 Atlas represents a type of object we will see more of as our detection capabilities improve. Long-period comets from our own Oort cloud, objects with orbital periods of thousands or millions of years, are considered pristine samples of early solar system material, largely unchanged since formation, but they still spent their entire existence within the Sunday's gravitational influence, occasionally perturbed by passing stars or giant molecular clouds, altering their orbits. Interstellar comets like 3 Atlas may have spent millions of years in true interstellar space, unaffected by any star, preserved at temperatures close to absolute zero, making them even more pristine samples of protoplanetary disk material. The age of 3 Atlas is particularly intriguing. We cannot directly measure its age, but we can infer constraints. If the comet traveled in interstellar space at its observed speed for millions of years, it has covered distances of tens or hundreds of light years. When the comet was ejected, the star system where it formed might have been closer to our solar system, and the Milky Way's rotation has since carried that system to a different region of the galaxy. Alternatively, the comet might have been ejected from a system now far away, and its long journey coincidentally brought it to our neighborhood. Either way, we are looking at an object potentially older than some surface features on Earth, a piece of cosmic history frozen in time. These implications extend to our understanding of how matter and information propagate in the galaxy. If interstellar comets are common, if they are occasionally captured into orbits around stars rather than just passing through, they represent a mechanism for transferring matter between star systems. A comet ejected from one system, carrying ice and organic molecules formed in that system's protoplanetary disk, might be captured by another system millions of years later, delivering these molecules to a completely different environment. This process, in its most extreme form known as lithopanspermia, has been proposed as a potential mechanism for spreading life or its precursors between star systems. I am not saying 3 Atlas carries life. The chances of any biological material surviving millions of years in the cold, radiation, and vacuum of interstellar space are essentially zero. But complex organic molecules, the chemical building blocks used by life, might survive. If comets like 3 Atlas regularly travel between star systems, they mix and distribute these organic molecules throughout the galaxy, potentially influencing the chemical composition of the planetary systems they visit or are captured by. The galaxy is not just a collection of isolated star systems, but a connected chemical network with matter cycling over vast timescales. This discovery also highlights the gaps in our current knowledge and capabilities. We detected 3 Atlas relatively close to perihelion, which gave us a good observation window, but also means we missed the opportunity to study it as it passed through the outer solar system, cold and inactive future detection systems. Particularly the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, expected to begin operations in the coming years, will detect interstellar objects much earlier, giving us months or years of advance notice. This early warning will allow us to plan dedicated observation campaigns, and perhaps even execute spacecraft missions to intercept and study these visitors up close. Imagine what we could learn from an interstellar comet mission. We could directly sample the ice, measure isotope ratios, revealing the temperature and chemical details of the protoplanetary disk where it formed. We could analyze organic molecules with laboratory instruments far more sensitive than telescopes. We could see the nucleus structure, understand its composition layer by layer, and directly test theories about how comets form and evolve. Several mission concepts to intercept interstellar visitors have been proposed, though none have been funded yet, but 3 Atlas and similar objects make the scientific case for such missions increasingly compelling. The radio detection also shows that we don't need to wait for dedicated space missions to learn about interstellar visitors. Ground-based observatories, with increasingly sophisticated instruments and coordinated observation strategies, can extract a wealth of information from these brief encounters. The key is preparation, having observation plans ready, allocating telescope time, and coordinating internationally to maximize coverage. The success with 3 Atlas shows that this approach works, that we can mobilize the global astronomical community to focus on these rare opportunities and produce high-quality scientific returns. However, even as we celebrate what we have learned, I am acutely aware of how much remains unknown. Every answer leads to new questions. Every measurement reveals gaps in our understanding, which is why this field is so exciting, dynamic, and full of potential for future discoveries. The study of interstellar objects is still in its infancy, with only 3 confirmed examples and limited data for each. But the trajectory is clear as our detection capabilities improve. As our instruments become more sensitive, and as our understanding deepens, we will detect more of these visitors, study them in greater detail, and build a comprehensive picture of the interstellar population. 3 Atlas is a milestone in this journey, not the destination. The unsolved mysteries it leaves behind may be more valuable than the questions it answered. Let's talk about what we don't know, because despite all the data we collected, all the insights gained, 3 Atlas remains in many ways a mystery wrapped in ice and rock, a traveler from an unknown origin, carrying secrets we are only beginning to uncover. Acknowledging these gaps in our knowledge is not a weakness. It is how science progresses. It is how we identify priorities for future efforts and the most important questions. So let me take you through the mysteries that keep astronomers up at night, the puzzles that 3 Atlas still presents, even after months of intensive study. The most fundamental unsolved mystery is where exactly 3 Atlas came from. We can backtrack its trajectory and determine the general direction, somewhere in the direction of the Draco constellation. But this does not pinpoint the specific parent star. The challenge is that the comet may have traveled for so long that the star system where it formed has moved significantly due to galactic rotation and its own proper motion through space. Even if we knew the exact direction the comet entered our solar system, tracing that line back millions of years requires accounting for the complex gravitational dynamics of the galaxy, perturbations from passing stars, and uncertainties in the comet's trajectory before encountering our Sunday. The parent star could be anywhere within a volume of space hundreds of light years wide. Some researchers are trying to narrow down the candidates by looking at the comet's composition and comparing it with theoretical models of star systems with different characteristics. For example, if we could measure the deuterium to hydrogen ratio in the water ice, that would tell us the temperature conditions where the ice formed, which correlates with the distance from the star. If we could measure other isotope ratios like oxygen 18 to oxygen 16 or carbon 13 to carbon 12, we could constrain the chemical evolution of the protoplanetary disk. But these measurements require spectral precision that is challenging for a fast-moving, distant object, especially now that 3 Atlas is receding and fading. Another mystery is how 3 Atlas was initially ejected from its parent system. Gravitational interactions with giant planets can kick comets to the outer regions of a star system, or even eject them completely into interstellar space. This is likely how most interstellar comets form, but the specific dynamics matter because they determine the speed and direction of the ejection, which in turn affects the comet's final location millions of years later. Was 3 Atlas ejected during the formation phase of its star system, when planets were still migrating and gravitational interactions were chaotic? Or was it ejected later by a close encounter with a rogue planet or during a stellar flyby? We don't know. Without knowing where it came from, we cannot reconstruct its history. The internal structure of 3 Atlas remains largely unknown. We observed the surface and the coma. But what lies beneath? Is the nucleus homogeneous, a uniform mixture of ice and rock, or layered, with different compositions at different depths, reflecting changing conditions during formation? Does it have large voids, fragile areas that might cause it to fragment if heated too strongly? The observed outbursts suggest structural heterogeneity, but we cannot image the interior with current technology. Understanding the internal structure is important because it affects how the comet responds to solar heating, how it outgasses, and ultimately how long it can survive as a coherent object. The rotation state and its evolution add another layer of mystery. We know 3 Atlas is tumbling, but the precise rotation period and axial orientation are uncertain. Furthermore, outgassing produces torques that change the comet's rotation over time, potentially causing it to spin faster, slower, or change its axial orientation. For 3 Atlas, these outgassing torques are particularly interesting because they are asymmetric, changing as different parts of the nucleus are heated. Did the rotation state change during the months it passed perihelion? If we could measure this change, it would tell us about the distribution of active areas on the surface, the efficiency of outgassing in different regions, and the nucleus's response to thermal stress. There is also the question of how pristine 3 Atlas really is. I mentioned that interstellar objects might be more pristine than solar system comets because they have been isolated in cold space for so long, but pristine does not mean unchanged. Interstellar space is not empty. It contains gas, dust, and high-energy cosmic rays. Over millions of years, even a small flux of these particles can alter the surface chemistry, break down complex molecules, sputter away material, or create new compounds through radiochemistry. How much has the surface of 3 Atlas been processed during its interstellar journey? Does the surface composition still reflect its formation environment, or has it been modified into something new? The hydroxyl detection answered some questions, but also raised others. The emission intensity tells us the water production rate, but it doesn't tell us the distribution of water ice within the nucleus. Is the ice concentrated in certain areas? Is it uniformly mixed with dust and rock? The fact that we detected hydroxyl confirms a significant water content, but the detailed spatial distribution of water affects how we interpret the observations and our inferences about the formation conditions. Future radio observations with higher angular resolution might be able to map the hydroxyl emission across the coma, revealing which parts of the nucleus are most active, but for 3 Atlas, we do not have that level of detail. Another interesting question is whether 3 Atlas visited other star systems before visiting ours. An object traveling at 15 kilometers per second in interstellar space for millions of years can cover vast distances, possibly passing near other stars during its journey. If it did those encounters alter its trajectory or cause heating events that changed its surface? Some simulations suggest that even in interstellar space, close stellar passages could temporarily activate outgassing if the star is bright enough and close enough. Any such event would be brief, but it might leave signatures in the surface structure or composition that we might detect if we knew what to look for. The fate of 3 Atlas is also uncertain in some ways. We know it is on a hyperbolic trajectory that will take it back outside the solar system, but where will it go next? Its speed and direction after leaving our system will determine which region of the galaxy it traverses next, whether it might encounter another star system in the foreseeable cosmic future, and where it will eventually be billions of years from now when our Sunday runs out of fuel. Backtracking the trajectory is hard. Predicting it forward is even harder. Because we cannot predict the gravitational perturbations it will experience along the way from unseen rogue planets, brown dwarfs, or stellar encounters. I am also fascinated by what we did not detect. Throughout the observation campaign, astronomers were alert for any unusual emissions, any unexpected signals that might indicate compositions or activities we have not seen before. But everything detected falls within the range observed in solar system comets. Does this mean interstellar comets are indistinguishable from our own? Or does it mean our instruments are not sensitive enough to detect subtle differences? We can only measure what our technology allows, and there may be chemical or physical properties of 3 Atlas that remain hidden simply because we do not yet have the right tools to see them. The comparative study of interstellar objects is still limited by small sample size. We have only confirmed 3, Oumuamua, Borisov, and now 3 Atlas. This is not enough to draw broad conclusions about the diversity of the interstellar population. Are these 3 representative of typical interstellar objects, or are they outliers that happen to be detectable? We won't know until we have studied dozens or hundreds of interstellar visitors, which will take years or decades of continuous surveys and observations. Each new detection will either confirm patterns or reveal new diversity, gradually building our understanding of what is typical and what is unusual. There is also a meta-question about observation strategy. Was our study of 3 Atlas optimal, or in hindsight? Would different choices have yielded more valuable data? Should more telescope time have been allocated to radio observations rather than optical? Should we have prioritized spectroscopy over imaging? These are not criticisms. They are honest reflections on how we allocate limited resources when studying rare, fleeting opportunities. Each interstellar object detection is a learning experience, informing how we handle the next one. gradually refining our methods and priorities. Finally, there is the biggest question of all. What will the next interstellar visitor reveal? Will it be similar to 3 Atlas, reinforcing the patterns and confirming the theories? Or will it be drastically different, forcing us to reconsider our assumptions about what interstellar objects can be? The universe has a habit of surprising us, presenting phenomena we did not predict or anticipate. Remaining open to these surprises while maintaining scientific rigor is the challenge we face with each new discovery. These unsolved mysteries are not setbacks, they are invitations. They are doors to future research, new observations, and deeper understanding. They remind us that science is a process, not a destination. We study interstellar objects not to end the mysteries of the universe. We study them to open new chapters, ask better questions, and push the boundaries of what we know into the vast realm of what we have yet to discover. In this context, 3 Atlas is not the end, it is a beginning. A glimpse of the richness that awaits us as we continue to explore the objects that pass through our solar system, carrying information from distant corners of the galaxy. To truly appreciate 3 Atlas, we need to place it in the historical context of interstellar object detection, a field that began with the still controversial Oumuamua. In October 2017, the Pan-STARRS telescope in Hawaii captured this first confirmed interstellar object. Its name, Hawaiian for scout or messenger, aptly foreshadowed how it would revolutionize our understanding of interstellar visitors. Its hyperbolic trajectory clearly proved its alien origin, but subsequent observations raised a series of puzzles. Brightness variations revealed an extremely elongated shape, like a cigar or a pancake. The surface reflectivity was unusually high, and most mysteriously, its trajectory showed a slight acceleration, unexplained by the Sunday's gravity. This anomalous acceleration sparked intense debate in the astronomical community. Some proposed outgassing, a rocket effect from material ejection similar to comets, but a coma or tail was never observed. More radical speculations followed: a light sail pushed by solar radiation, a fragment of a Dyson sphere, or even an alien probe. The mainstream scientific community still favors natural explanations, speculating it might be composed of solid hydrogen or nitrogen ice, which outgasses without producing a visible coma. But the lack of conclusive data leaves room for speculation. Oumuamua taught us the most crucial lesson: humanity was completely unprepared for interstellar visitors. It was discovered after perihelion, accelerating away from the solar system. We only had a few weeks to observe it, far from enough to solve all its mysteries. This rush, though regrettable, forced the scientific community to upgrade detection capabilities and develop rapid response protocols, paving the way for the study of subsequent interstellar objects. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered the second interstellar object, 2I Borisov, which stood in stark contrast to Oumuamua. From the beginning, it exhibited clear cometary features: a visible coma and tail, spectra detecting water vapor, carbon monoxide, and other molecules common in solar system comets, and brightness changes with solar distance fully consistent with expectations. This textbook performance relieved astronomers, confirming that at least some interstellar objects are just ordinary comets that happened to wander into the solar system. More fortunately, Borisov was discovered months before perihelion, allowing ample time for observation. Astronomers coordinated multiple instruments to track its entire journey, collecting far more complete data than for Oumuamua, and completing the first detailed chemical analysis of an interstellar comet. Surprisingly, its composition was highly similar to many solar system comets, suggesting that comet formation processes might be universal across different star systems. But its uniqueness was also significant. The ratio of carbon monoxide to water was higher than in solar system comets, and its structure was more compact and dense, pointing to the possibility of formation in a colder environment or a different type of star system. Now, the appearance of 3 Atlas gives us a third crucial data point, and the family portrait of interstellar objects is gradually becoming clearer. They are not all Oumuamua, like anomalies. Most may be normally behaving comets, distinguished from solar system objects only by their hyperbolic trajectories and subtle compositional differences. The hydroxyl signal of 3 Atlas reinforces this pattern. It has the outgassing behavior of a comet, follows known physical laws, yet carries the chemical code of another star system. This extraordinary within the ordinary is the core of its scientific value. Comparing these 3 objects, diversity is already apparent. Oumuamua remains an unsolved mystery, with the issues of anomalous acceleration and lack of outgassing traces not fully resolved. Borisov is the standard model, active and predictable. 3 Atlas falls somewhere in between, with normal cometary activity, but carrying unique features like high carbon dioxide content and unstable brightness. Even with a sample size of only 3, it is enough to show the richness of the interstellar population. They form under different conditions, evolve along different paths, and present vastly different challenges for observation. Besides these 3 confirmed cases, interstellar object detection is also filled with suspected signals and false alarms. Survey telescopes often find objects with orbital parameters suggesting interstellar origin, but as observational data improves, most are reclassified as solar system objects. The difficulty lies in the extremely high precision measurements required to determine if an orbit is truly hyperbolic, especially for objects with speeds close to the bound versus unbound boundary. As future detection capabilities improve, we may encounter more borderline cases that require extensive observation to confirm their identity. More thought-provoking is, how many interstellar visitors have we missed? Existing detection systems are significantly biased towards large, bright, near-Earth objects. Small, faint, or distant objects easily remain invisible. Statistical models show that several interstellar objects may pass through the inner solar system each year, and if we include the region beyond Neptune's orbit, the number could reach thousands, most passing by quietly in places we cannot see, carrying unreceived cosmic information. Here we must mention the fascinating connection with SETI, search for extraterrestrial intelligence. When we talk about receiving the 3 Atlas signal, the language used is identical to the scenarios of SETI scanning for artificial radio signals for decades. SETI has detected many candidate signals, brief, strong emissions that sparked fantasies of first contact, but ultimately either could not be reproduced or were confirmed as ground interference or natural phenomena. The hydroxyl signal of 3 Atlas is completely different. It is a verified natural emission with a clear physical origin, but the emotional curves triggered by both are highly similar. The excitement of detection, the speculation of meaning, the satisfaction of final understanding. The rigor SETI taught us also applies to the study of interstellar objects. Excitement cannot replace careful analysis, and extraordinary claims require extraordinary evidence. The progress in interstellar object research also benefits from the synergistic development of other astronomical fields. Exoplanet research has exploded in the last 20 years. The discovery of thousands of exoplanets has revealed the diversity of planetary types and orbital configurations, providing references for speculating the parent system background of interstellar objects. Protoplanetary disk research, aided by high-resolution imaging from telescopes like ALMA, allows us to see disk gaps, ring structures, and molecular distributions. When we detected the high carbon dioxide content of 3 Atlas, we could combine this with protoplanetary disk observation data to infer that its formation location might be in the outer regions of its parent system. And the next frontier in this field is likely direct spacecraft detection. For years, scientists have proposed various mission concepts, launching small probes to intercept interstellar objects for close-up observation or even landing. The technical challenges are obvious. Interstellar objects are extremely fast and often discovered close to perihelion, leaving very little time for launch. But these challenges are not insurmountable if future detection systems can provide several years of warning, or if rapid launch spacecraft are developed. The feasibility of such missions will increase significantly. Imagine the breakthroughs a spacecraft could bring: high-resolution imaging of nucleus details, direct sampling of coma gas analyzed with laboratory precision, accurate measurement of isotope ratios revealing the formation environment, or even returning samples to Earth. This data could completely rewrite our understanding of planetary system formation. Even without spacecraft, the next generation of observation equipment is on the way. The Vera Rubin Observatory's Legacy Survey of Space and Time will scan the entire sky weekly, automatically flagging objects with anomalous trajectories, providing months or even years of warning. The Square Kilometre Array SKA, under construction as the most sensitive radio telescope, will be able to detect molecular emissions in greater detail, map the distribution of coma gas, and capture faint signals currently undetectable. But technology is just the foundation. Global collaboration is key. The successful study of 3 Atlas is the result of coordination between professional observatories, amateur astronomers, and research institutions. Amateur astronomers' 24 observations filled the gaps of professional equipment, and international data sharing maximized analysis efficiency. As the number of interstellar object discoveries increases in the future, Rapid response networks, real-time data sharing, and cross-time zone observation coordination will become more important. Public participation is also indispensable. The mystery of interstellar objects easily sparks public curiosity, and this enthusiasm can be transformed into research support and encourage more young people to enter the field of astronomy. From the story of 3 Atlas, we can take away not only scientific knowledge, but also a mindset of rational exploration, following evidence rather than speculation, accepting the scientific nature of answers leading to new questions, and understanding that the complexity of nature far exceeds simple narratives. This icy rocky comet drifted in interstellar space for millions of years, coincidentally entered the solar system, and was discovered just when we had the technology to detect it. This is not science fiction, but a scientific fact more profound than fiction. Now 3 Atlas is moving away from the solar system, its brightness decreasing weekly, but the legacy it leaves behind will continue to ferment. The methods used to study it will be applied to the next visitor, and the puzzles it posed will guide future research directions. And based on the frequency of 3 confirmed detections in just a few years, the next interstellar visitor will inevitably arrive. The only questions are when and in what form. Each of us is a participant in this exploration. When we look up at the night sky, we see light traveling from billions of miles away. When we learn about the journey of 3 Atlas, we are deepening our connection with the universe. The signal of 3 Atlas is not a greeting from an alien civilization, but a letter written by the universe in the language of chemistry and physics, telling us that we live in a connected galaxy, and human curiosity and rigor are bringing more cosmic mysteries to light. The next messenger is already on its way, and we are ready.